Welcome back, students. So, in the last video, we talked about the basic laws for electromagnetic field theory. So, in this video, we'll be continuing with the electromagnetic field theory, right? So, what was let's just revise the outline. It was introductions, Maxwell's, equations in differential form, Maxwell's equation in integral form. Then we talked about the prerequisites as we did the revision on Gauss's law of electrostatics, Gauss's law of magnetostatics, Faraday's law of electromagnetic induction, Ampere's circuital law, Gauss divergence theorem, Stokes theorem. These theorem we'll be using in deriving Maxwell's equation. We also talked about the application of EM waves because as I said, if we are starting with a unit, you should know why we are studying that unit, right? So there are so many applications of electromagnetic waves. If I am able to communicate to you, then that is also because of the application of electromagnetic waves via this video. Okay. So now let us talk about electromagnetic field theory. So if I give the introduction, then what is electromagnetic? Electromagnetic is the branch of science concerned with the forces that occur around electrically charged particles and the relation between those forces. Okay. So in the formulation of electromagnetism, Maxwell's described light as a propagating wave of electric and magnetic fields. And he also, showed that the speed of the light is equal to 3 into 10 to the power 8 meter per second. So if I just write down the gist, then what is electromagnetic wave? Electromagnetic waves are created as a result of vibrations between an electric field and magnetic field. Okay, electric field and magnetic fields. And if we see, then we can also say that EM waves are composed of oscillating magnetic and electric fields, right? So generally, an electric field is produced by a charged particle. A force is exerted by this electric field on other charged particles. Positive charge accelerate in the direction of the field. Negative charge accelerate in the opposite direction of the field. A magnetic field is produced by moving charged particle. A force is exerted by this magnetic field on other moving particles. The force on these charges is always perpendicular to the direction of their velocity and therefore only changes the direction of the velocity, not the speed. So electromagnetic field is produced by accelerating charged particle. Electromagnetic, if we write down electromagnetic field is produced by an accelerating charged particles. Okay. So electromagnetic waves are nothing but electric and magnetic fields traveling through the free space at the speed of light. An accelerating charged particle is when the charged particle oscillates about an equilibrium position. So we can just say that electromagnetic waves can also be produced by electric current. So there we will also see the characteristics of electromagnetic waves, that how they are transverse in nature, and how these oscillating perpendicular to the direction of propagation, these electric and magnetic fields are propagating. So we'll be seeing all this. Now we will be starting with Maxwell's equation. See, Maxwell's introduced the four equations. Maxwell's first equations, Maxwell's second equation, third equation, and fourth equation. Now, what is Maxwell's first equation? I will just tell you that Maxwell's first equation, whether it is in integral form or differential form, it is representing Gauss's law of electrostatics that we revised in the last video. Maxwell's second equation, it represents Gauss's law of magnetostatics. Maxwell's third equation, it is representing, now tell me what? Very right, it is Faraday's law. Maxwell's fourth equation, it is representing Ampere's circuital law. Therefore, we revised all these laws in the last video because the Maxwell's equations that we are going to talk in electromagnetic field theory, the electromagnetic field theory is based on these four equations. The pillar of electromagnetic field theory are the Maxwell's, all these Maxwell's four equations, and these four equations are based on the basic laws that we talked about, that is Gauss's law of electrostatics, Gauss's law of magnetostatics, Faraday's law, Ampere's circuital law. So the significance of these laws are not changing. It is changing. It is the Maxwell's, we represented these laws in mathematical, differential, and integral form. So now let us see Maxwell's equations, how we are going to derive these Maxwell's equations. So first we will be deriving with Maxwell's first equation. Okay. So let us write down the topic. Maxwell's first equation in differential form. In differential form. Maxwell's first equation in differential form. Okay. Now let us see how what I said in the last slide, that Maxwell's equation first is based on Gauss's law of electrostatics. So according to how we will start is law according to Gauss's law of electrostatics. The total flux passing through a closed surface as in vacuum is equal to 1 by epsilon naught times the total charge Q enclosed. So what is phi E equal to? Phi E is equal to Q by epsilon naught, where epsilon naught is the permittivity of free space. And if we talk about any medium, then this phi E will be represented in terms of phi E is equal to Q by epsilon, where epsilon will be permittivity of that medium. Okay, of the medium. Fine. We can also represent this phi E in terms of electric field. Okay. So how we can represent this in terms of electric field? This we can represent phi E is equal to surface integral E dot ds. It means what? That surface integral E dot ds is equal to Q by epsilon or if we are talking about free space, then Q by epsilon naught. So now mark this as equation number 1. We can also represent this Q in terms of volume charge density. Okay, this is charge Q. Then Q can be represented in terms of volume charge density. How we can represent it? Then I'll just show you. See, if charge Q inside the closed surface is continuously distributed, and rho is the volume charge density, then how we can represent this? Very right, Q is equal to volume integral rho dV. So now mark this as equation 2. So equation 1 is surface integral E dot ds is equal to Q by epsilon. So now from equation 1 and 2, what we get? We can write this as surface integral E dot ds is equal to 1 by epsilon Q by epsilon tha. In place of Q, what we can write? Volume integral rho dV. Okay, so this is equation number 3. Now, next, what we will do is, we will be using Gauss divergence theorem over here. What we will do is, we'll be using Gauss divergence theorem. This also we revised in the last video. See, I said we'll be using. So now we are using Gauss divergence theorem in Maxwell's first equation in differential form. So according to Gauss divergence theorem, what it is? That it can convert surface integral into volume integral. So we can convert this surface integral E dot ds to the volume integral del dot E d. Okay, this is equation number 4. Now, if we see, we can put this in equation number 3. So from substituting in equation 3, or we can write from equation 3 and 4, what we get? If we substitute this volume integral in place of this, we get that volume integral del dot E dV is equal to 1 by epsilon volume integral rho dV. And from this equation number 5, what we get is that del dot E, because both side is the volume integral, then these quantities, we know that del dot E will be equal to rho by epsilon. Okay, so this is nothing but the Maxwell's equation in differential form. This is the Maxwell's equation in differential form. And this equation is, because it is representing Gauss's law of electrostatics, therefore it is Maxwell's first equation in differential form. We can write this Maxwell's first equation in differential form also in this manner, because we are writing over here del dot E is equal to rho by epsilon. So del dot epsilon E is equal to rho. And what is epsilon E? This represents D. That is the displacement vector. It represents displacement vector. So what we can write? Del dot D is equal to rho. This is also Maxwell's first equation in differential form. in differential form. So both these equation, this equation plus del dot E is equal to rho by epsilon. Both these represents Maxwell's first equation in differential form. Okay, using this operator del. Okay, so these are the Maxwell's equation, and what these signifies? This signifies Gauss's law of electrostatics. The significance is not changing. It is the Maxwells who represented that law in differential form in a mathematical manner. Okay, students. So in the next video, we will be talking about Maxwell's second equation. And we will be seeing that how it is also representing Gauss's law of magnetostatics. Thank you, students. We will be meeting again with Maxwell's second equation in differential form.